The final session of today, which is a discussion session. So we'll start, I think, again with some time in case there's any more questions on the talks of today, and then we can go over into discussing kind of some of the open questions, either from or for the theory community. Yeah, so I would kind of encourage maybe all the speakers of today and also the kind of the theory speakers of the other days to have the videos on if they feel comfortable with that. And then you can, everybody in the individual Zoom settings, you can choose the option show only video participants. So you right click on somebody who doesn't have a video and you do hide non-video participants, and then you should kind of see a nice gallery view of the speakers. And of course, if you're asking a question or you want to participate, you're very welcome to turn on your video also, so that we can see who's talking. Okay, so let's start. So are there any more questions regarding the talks of today? I see your first question by Danny.
Yes, hi, can you guys hear me? I guess yes. It's a question for Sebastian Kles, if he's around.
Yes, I am.
Hello.
Hello, Danny. How are you doing?
Hello. I have a couple of questions, actually. The first one is, I think you show at some moment some spectrum that look like a scale invariant in omega gravitational waves. And you said this came from a distribution of very ultralight primordial black holes, if I remember correctly right now. I was very interested in understanding what the spectrum is this, no? Because something scale invariant spanning so many decades typically points to scaling sources for a scale invariant
exactly. So it's a
so how does this come about?
Spectrum. Yeah. It's a nearly scale invariant primordial power spectrum, and in particular in the plot that I've shown, it's exactly scale invariant. This is the model by Tony Riotto and others. So in their particular case, the mass of the black hole stops at the asteroid mass, but if the power spectrum is really scale invariant or nearly scale invariance on a very broad range of scales down to very, very small scales, then you would produce, due to second order perturbations, this gravitational wave background.
So you are saying that they are enhancing scalar perturbations as a scale invariant.
Exactly.
And what's the mechanism to do that? Because normally when you enhance them, you produce a peak in the power spectrum if you have a special feature in your potential.
So this is when you have a special feature, but you can also simply have like two phases of inflation. Or so it's always possible to produce this kind of nearly scale invariant power spectrum.
So what I find a bit confusing is that it's possible to produce such large fluctuations while maintaining the scale invariance. You know, that's for so many decades. That's what I find curious, because normally, precisely to enhance the fluctuations, because you need something special that breaks the scale invariance. You know, and that's why I find it a bit funny. But you say it's a paper of
so the idea behind these models is more to have, I think, two phases of inflation. In fact,
inflation, but I don't know. In my mind, I don't see how that anyway gives rise to such a elongated spectrum. Okay.
And I know it's not so easy. In fact, because in the scalar power spectrum, you have the two Slorol parameters that are there.
Yeah.
And so if you want an exact scale invariant, that means that typically you have the first Slorol parameters very, very small. Okay.
Well, in a slow roll, yes. I mean,
but then you produce manifolds during this second phase of inflation, and so in that case you would have the last 60 folds quite naturally in this second phase, and so this is
okay.
So this would need some fine tuning of the inflationary model that could produce that.
But typically, for instance, if I just consider a standard quasi de Sitter slow roll inflation. The amplitude of standard fluctuations in second order to gravitational waves, they give a very subdominant background of gravitational waves. But
Yeah,
you
yeah.
show
So in
something
that case,
very
in these models that I mentioned, you have a higher amplitude on small scales than on large scales. So you have typically, let's say, two phases of inflation, one producing the CMB scales at a very low level, and one producing a much larger power spectrum.
Okay, I'll have to read about it because I really don't
Can
understand.
I comment here,
Yeah.
Danny? So indeed, there's a lot of fine tuning because you have to do this two-step argument for having essentially scaling variant, but at two different scales. And you're right that it's very difficult to keep the second stage sufficiently flat for sufficiently long. And that's the main point.
And not
there are
long,
some scenarios where you have how to say, expectator fields, which are massless. And this produce something like an iso-curvature fluctuation, which keeps on being essentially scaling variant. This produces on the, so when it re-enters the horizon, a gravitational wave background, which also would be essentially a scaling variant. It is rather fine-tuned because, as Sebastian correctly said, if you keep on for so long, you're already eating many of the e-folds that you associate with the CMB scales. So you would have to make those two large steps, one for the CMB and another one for primordial black holes, have a very fast transition from one to the other without affecting large scale structure. Things like Lyman alpha clouds, for instance. So it is fine-tuned. It is very difficult to
So it is a spectator field with this kind of examples with a speed of sound different than the usual case, what they are using to produce this large.
I'm not sure. I'm not sure exactly what kind of scenario they have.
No, it's more a phenomenological scenario. Huh? So it's not using a particular model, but you can use the standard formalism to do that. You can use the standard floral formalism to do that.
Okay, I'm just surprised, honestly, but okay, yeah. I'm sure.
I was also very surprised. I think we should take with a grain of salt the length, so the width of the scale for which this remains.
Okay. Have it put by hand, perhaps. Okay. Well, anyways, thanks. I have a second question for Sebastian.
Yeah.
You were mentioning in the second part of your talk when you proposed this very interesting new approach, that there are simulations to confirm some of the estimations you are making. So maybe you can show the transparency where you are mentioning this. Just wanted to ask you what simulations are we talking about here?
Yeah, I was thinking of simulations that have been done by Nicolas Herman with one of the others here.
Yeah.
And so what he did is really to compute, to take the waveform. So where is it, the waveform? I think I have put the waveform somewhere. Here. So you take the waveform and you pass it through the detector. And so you simulate in output what will be the power that you gain in the cavity. And so that's the kind of simulation that
what equations are you simulating? Sorry, that's just.
And so the equation that you are simulating are the one of the inverse Gerstenstein effect with a gravitational wave that is so this is this equation, but simplified in the case of static B field and a plane wave equation. And so we are simulating these equations. Well, then it's a bit more complicated because it becomes more technical, because you have to expand in some polynomials the resonant modes that are excited in the cavity, and then you sum over all the modes. And so it's a little bit technical, but it can be done with just a simulation.
The point is, I see this kind of equation, Sebastian, and I think this would be totally suitable for a lattice simulation in 3D, and I was wondering if that's really what you mean by simulation.
No, well, what we did was not in 3D, but it could be done in 3D, yes.
Yeah. Well, I mean, if this is what you need to simulate, I mean, this is totally suitable for kind of lattice codes I have, that you could certainly set a background magnetic field and the perturbations, then gravitational wave and all of that. With I assume you have some cylindrical symmetry here.
Yeah, yeah. Then you would be able to do even something more complex that what we have done, because
you've done it in 1D, right? Yeah. Okay. Yeah, I think it can be done in 3D. Honestly speaking, I don't know if this adds much or not, but it could be fully done if this is really the system of equations. I mean,
yeah, and you can take then a gravitational wave that is not in the Z direction and see
I mean, you could put a plane wave coming from arbitrary direction, of course.
Yeah. That would be interesting. Yes, certainly. I don't know if Nicola is there and wants to comment, but Nicola, yes,
I am here.
You did the simulations.
Yes, the wave equation is solved by a spectral method. So we reproject the wave equation in 3D on the proper function of the Laplacian, and we get a temporal 1D equation for the spectral coefficients.
Yeah, I see. Yeah, well, my point is, I think one doesn't need to do that. You can do the full 3D simulation of those equations with current numerical technology with no problem, I believe.
Absolutely, but the advantage of using a spectral method is to that the proper function automatically satisfies the boundary condition of the cavity.
Yeah,
so
okay,
this gives the absolute certitude that we have the boundary conditions.
Right. I see the point.
And this allows to see also the modes that are exciting.
And probably so with axions, we are doing my student was doing axion electrodynamics, and I mean this is now gravito-electrodynamics.
Yeah.
And then you could use commercial packets like COMSOL, where people simulate all the cavities are simulated by COMSOL, and there are packages where you can modify, so to say, the partial differential equations which are solved and so on, and there are you can have all the boundary conditions and everything is in that. So in principle, I think you do not have to invent the thing from scratch. It's already there. But things are already there. I mean, so they are doing 3D simulations of the cavities and they're calculating all the things. So what
we did was more simple than that. So certainly this can be done with this kind of codes, yes, in 3D with a full design of the cavity.
So is it do you need numerical simulations even to solve them in the frequency domain? Because I would imagine that with some approximations, you could get at least some analytical solutions in the frequency domain.
In the case of our article, now if we use a frequency domain approach, the solution is analytic.
Okay, so then there you go.
Yes.
Yeah. Okay. Nothing needed. Okay. Very good.
Nancy, did you have another question because you had your hand up?
Yeah, I had a question for Clive. So I think first a clarification. I now understand the source of my original confusion. I think the B, Z, and you're also assuming the propagation as a parallel to B. And now I understand why I was having a problem with the directions of the photon flux. So I don't know how to generate such a field, and I imagine maybe other people do. I am not a microwave person. But the other thing that I was confused by was the reflector. So why does one need a reflector? Because if the applied RF field is going in Y, and if the generated photons are generated with the traveling direction of X, you can just wait until they're outside the beam, or why?
Yeah. In principle, you don't need any reflector. The idea of putting reflectors in was to try to direct the PPF, that's the photons that correspond to the signal, to somewhere else where the spillover from the transmitter is less. And people have fooled around with various configurations of that, and I don't know that it really helps a lot, really.
But presumably the generation direction of the photons is already at the minimum. If it's exactly perpendicular to the applied field, that's where you should have the minimum spillover from the Gaussian beam.
Well, no, the spillover itself is isotropic in the XY plane. So what you might try and do is to reflect the PPF to somewhere else, or concentrate it or focus it in some way, so that it minimizes the interaction between the transmitter and the detectors. But I don't know that it really helps a lot in practice.
Okay.
I mean, for example, you could envisage some system of reflectors that direct the PPF so that it's now going downwards in total opposition to the incident electromagnetic beam. And then you put your microwave detector so that it's looking upwards. So then you've now directed your PPF downwards. You put your receiver here, and then of course the main gravitational wave is going upwards, and so you hope that the receiver doesn't receive it. But I suspect, unless you're going to do this in a very clever way, that the requirements are so stringent that I don't know that it would help a lot to do that.
Okay.
Eugene, please.
Yeah, hi. I mean, maybe I change the topic a little bit. I always have I've been watching and really enjoying this conference. But one of the things that maybe just a question out to both the theory and the experimental community as a whole is that it seems that there is a focus, or it could be on looking for stochastic gravitational waves for all the phenomena. I mean, is that a thing that is imposed to us by our experimental limitations, or is just the way that this is just the direction that the field is going? I mean, the reason I ask is that when you want to do stochastic gravitational wave, you need to understand populations, right? Like, and it's not necessary that you will see the stochastic gravitational wave first. For example, we saw binary black hole mergers, the coherent signal. We haven't seen the background yet. So so is that just a choice of community, or it is just it is some actual experimental constraint that we should be looking for stochastic, not coherent signals?
So who would like to reply? I can try to reply. I can start. Well,
I can have a go as well.
Yeah, please go ahead.
Well, you go ahead. You spoke first, and then I'll add something when you finish.
For me, the problem is that you don't have sources that are not exotic for let's say transient sources like gravitational wave mergers. So we had this idea of primordial black holes, and with small primordial black holes it works, but they are still hypothetical. And so it's difficult to get high frequency gravitational waves with compact objects, because they need to be very light, and so that's not so easy. And so usually people then move to the stochastic backgrounds, because then you are probing very high energies in the universe, and so this is the place where you can have many new phenomena easily, like phase transitions, I don't know, preheating, oceans, or even primordial black holes as well. And so I think that's the main reason why people are looking for a stochastic background. It's just a question that we don't have really sources at high frequencies.
Maybe just a comment that, I mean, in the white paper, we actually discussed both options, right? So we discussed, I mean, everything requires new physics in this frequency regime, right? And then if you, I don't know, if you prefer a super radiant signal over a phase transition signal, is maybe also a bit a matter of taste. But personally, I think it's important to, well, it's kind of important to do both, maybe.
Yeah,
but I
so.
think it's also very important. So if you have an experimental, okay, if you have a theory source, then you kind of say clearly what sort of a source are you actually, like, what sort of gravitational waves are this? What are you expecting? But also on the experimental side, right? If you claim you have a sensitivity curve, to make it kind of clear, what is it referring to, right? Is it referring? Is this particular experimental setup better suited for a stochastic background or for a monochromatic source? And I don't think that there's a uniform answer to that, right? I think it really depends on the setup.
And there are
That's
also
one.
continuous wave sources that could be interesting also to study,
Yeah.
and this is not.
Yeah, I think I see what you're saying. I mean, I think I can answer at least for a specific part on the light primordial black holes, though. I think for primordial black holes, as long as the primordial black holes, even if they're very, very light, right, you will have exactly the same signal as the very massive one, because the for primordial black holes, as long as the signal comes from like more or less equal mass merger, you can use exactly the same waveforms. You just scale it by mass.
Exactly.
So I think for primordial black hole, it's not a problem. But I can see that for some other stuff, you really need to do, you're saying that most of the exotic stuff we don't have waveforms models, because those are hard to calculate. Is that a fair comment? Is that a fair comment, or is just my interpretation of it?
Actually, let me comment here, since you mentioned these exotics. There's another source I will describe tomorrow, which is close hyperbolic encounters. They're not in spirals. They are also like a burst. Okay, it happens once, two black holes which happen to go near each other. Now, it's true that if you think of analogous situation with stellar objects, neutron stars in dense clusters, or you can think of even planets, no, in compact planetary systems, they would not generate frequencies because the process takes very long. It's more in Lisa frequencies for those masses. Even if the masses is small, you won't get that same frequency range. So I think in terms of exotics, I would argue that probably the best candidate that we have so far is reheating of the universe. We know it must have happened at some point. We don't know the reheating temperature. Therefore, I agree with you. We don't know what was the size of the horizon at the time that happened. And therefore, we don't know exactly whether it's megahertz, gigahertz, or even further, depending on the scale of inflation. So, but that's a stochastic. And let me comment then that it's probably easier for us to measure a stochastic background than a single event because of the integration in time. So we can keep on measuring that background for long enough. You mentioned LIGO versus, so individual event versus the background. That's because we've only been measuring for a few years now with LIGO. Once we've been a decade-long measurements with Lisa, for instance, it's much easier to see the stochastic backgrounds than individual events. So there's a trade-off in amplitude versus the integration time. So that's something which, for the moment, this is a very new area of research, and I'm sure eventually when gravitational wave astronomy is established, in 20 years, 30 years from now, it will be rather standard to look for stochastic backgrounds of gravitational waves.
Perhaps I could just add some comments to that. Everything that has just been said is true, I think. People have been thinking about exotic sources of high-frequency gravitational waves. And I mean, the list of colleagues that I had at the start of my talk are people who've thought about that fairly extensively and published some sort of feasibility studies of high-frequency gravitational wave generators. I think the problem is that the engineering problems involved in making a feasible gravitational wave source on Earth that has any kind of amplitude comparable to what one might think one could measure with one of these detectors tweaked to optimal sensitivity. The engineering problems in doing that are at least as daunting as actually making the detector itself. For example, I remember one proposal involved having hundreds of magnetrons spaced around a circle of several hundred meters radius, and they've all got to be phase coherent, and they've got to be driving enormous numbers of piezoelectric resonators, all of which have to be driven in phase. And you know, this is just a huge undertaking, and without a lot of design studies that haven't been done, one wouldn't want to undertake such a construction project. So therefore, what other sources do we have? And the answer is relic waves, which are stochastic, and you're trading the fact that a terrestrial source you can control, you can switch it on and off, so you know when it's going to happen, for the fact that the relic source is stochastic, and that brings with it its own problems. And plus, I think also, if you can make this work and you have a detector that will detect relic gravitational waves, that sounds sort of interesting to the wider scientific community. So I think there's also some aspect of advertising in play here.
Okay.
I see Axel has his hand up.
I would like to also point again at this transient sources like mergers of asteroid mass black holes. And there's also kind of low-hanging fruit that if someone really can calculate, let's say, the antenna pattern of ALPS 2 as a magnetic gravitational wave detector, then we could also maybe have some limits on mergers also. Just assuming that certain mass black holes are certain black holes of specific masses are the dark matter of our galaxy. And so I could assume if you have then the profile, dark matter profile of our Milky Way, we know the antenna pattern of ALPS, we know which kind of sky we trace during the day and the year, and then we can have maybe limit certain dark matter models. And this could be maybe comparable, easy to do, but I don't know the details, of course. But yeah, Valerie is it's not clear what I mean.
Yeah, no, it's clear what you mean, and we even started doing that computation once, not for ALPS, but just kind of asking the question like, how probable is it to see a nearby merger, right? Because you could say you have light primordial black holes, right? And you can kind of and if you get super lucky, you could have a merger super close by, right? And then you could actually detect it, right? And I think that's a real possibility. But the question is, how lucky do you have to be in order to have a really close enough merger?
I'm going to describe this tomorrow, Valerie.
Right, and the
happy
answer
to
the answer to that is very lucky, I think.
Well, not necessarily, but I'll describe.
Okay, I'm looking forward to your talk.
So even if you assume, for example, for simplicity, that all of the dark matter is made, let's say, by some asteroid black mass, mass black holes, that this is just all of the dark matter, then you also have to be super lucky.
This is my statement, but let's see what Juan tells us tomorrow.
Okay.
But it depends on the sensitivity that you would get.
Yes, of course, but like if you could kind of just compare to the typical what we have at the moment, right?
If you can go below 10 to minus 20, then maybe it's fine.
Yeah, but I think also like regarding this question of, I think it's a very interesting question, kind of stochastic versus individual sources, or like let's call them transient sources, because I mean I agree, right, with what Juan says, that you kind of, a stochastic source, you have an integration time, you profit from that. On the other hand, you have the intrinsic problem that you can't turn it off, right? So that it's and you can't shield it, right? So you need to be really, really sure that you're not measuring some noise. So I think that's a challenge.
Yeah, I guess I was thinking like more like rare events, right? So like you might have rare events where you have a huge signal that happen very rarely. Fair enough, right? You know, but they're so rare, even though they don't really add up to the stochastic. But like all sources are on a distribution, right? I mean, sometimes you get a very loud rare event, and if you look for those, maybe you get lucky and see one of these rare events. But if you're looking for the stochastic, maybe you missed it. So I was thinking about more along that lines, but I think I totally get what you're all saying, especially I think one point about total integration time is a good one. You profit from just sitting and waiting for a long time, if you like.
But I will discuss also the rare events tomorrow.
Okay.
And I can add like one other perspective to this question, which is, I think it doesn't really help to ask what can we do with the detectors so much as it's what are we interested in finding out. And there are definitely questions about cosmology that we will never be able to answer with coherent or transient sources. So from that perspective, we have to develop schemes to look for stochastic or analyze, to do stochastic analysis. Yeah.
Yeah, I think my point. I don't think I'm saying I'm not asking people to stop doing stochastic. I guess. Well, I guess what I'm saying is that they are both complementary windows, right? Either is they are not like if you do all stochastic, you will be able to figure out all the coherent physics. If you do all coherent or transient physics, you won't be able to figure out the stochastic physics. For example, like transient sources, unless you have lots of them, you won't understand the population, for example. But then stochastic is basically noise, right? You lose a lot of your signal is very, very low fidelity. You look at the internal structure of your sources. So in a way, they are both probing different regions. And I'm just wondering if the the focus on stochastic is we are missing out we're missing out a trick here.
Maybe to rephrase that question, maybe also to our experimental colleagues, I don't know, Axel or Aldo or so, would you say what's your feeling? Is it, what's more difficult, the stochastic or the kind of transient, more monochromatic sources?
I guess that transient, if we have a cross correlation, well, suppose that we have magnets as ALCI has, we use both cavities as gravitational wave detectors, and we see let's say a correlation that is transient. It's difficult to say that is a gravitational wave at that frequency, but there is a signal, so it's something that is on both of magnet, and they have to, and we need just the magnet to be on for that time. So it might be that, as Axel said, that ALPS has the possibility to, let's say, to exclude events on time and space where the magnet points, because we need gravitational wave to be perpendicular to the magnetic field. So if you imagine that the Earth is rotating and also are on this axis, and it's rotating also around the sun, you might say exclude part of events in the sky. Yeah, for a gravitational wave background still works this cross correlation, since gravitational wave background will generate, in my vision, some random noise, and this random noise will be present there. So you start to integrate in time, and there is, let's say, in this cross correlation picture, then there is a noise that you can't go below that. So that means that there is a stochastic background. So which is more probable or less? I don't know how to explain right now, but yeah, I think that ALPS has the possibility. By the way, you have YAXO. YAXO can point everywhere in this, somehow in some region of the sky, but can be modified to point where the interested say sources are, and use this magnetic conversion principle to exclude, let's say, high frequency gravitational waves, or even low frequency gravitational waves, let's say at gigahertz, if we have a detector that can collect the photons at gigahertz or terahertz. So it's very, let's say, adaptable to what physics you want to look for.
I would be a bit more vague. So I think when now switching on ALPS 2 for axion search, we'll learn much about really the background noise we have and how quiet we can get the detector. So when developing the optics for ALPS 2, we learned much about noise sources, which at least I was not aware of before. So some coating noise and surface roughness of mirrors and stuff like this, which causes scatter. So probably will, as I said, we'll learn much in the next 1 or 2 years about backgrounds, and then we can decide or maybe make a more qualitative statement for the ALPS 2 case, which could be targets for gravitational waves. How well we could have the electronic noise or the optics noise under control.
Actually, Axel's comment reminds me of the discovery of the CMB, right, by Penzias and Wilson. So you keep on lowering your sensitivity, eventually you see something which is isotropic, and it cannot be reduced. It's irreducible. So this brought me to a question. So are we sure all those stochastic backgrounds are really isotropic? If they come from preheating, I agree, they must be, because of the size of the horizon at the time compared to the area that you cover. But in the case of stochastic backgrounds from, say, dark matter, so primordial black holes as dark matter, we might see some anisotropy induced by the distribution in the galaxy. So that could be extremely interesting to find a background which is irreducible, and it has a correlation in the sky, which is telling you that it's really a nearby source, and it's not something cosmological. I think that would be extremely interesting. And of course, the angular resolution of these detectors is not something that is like LISA. No, we have to wait for the motion of the Earth around the sun, you know, to start to see real modulations in the signal. But it's a prospect. It's an interesting thought. No, can we see anisotropies in the stochastic background?
One comment.
Yeah, I think for this frequency range, right? I think this is going to take a while. we first need to get into a range where we can kind of make the leading order detection, right, before we get to anisotropies. But I do think you raise a very interesting point, right? Because I think there's also kind of the question, kind of as as theorists, if when we predict our sources, what are actually kind of the properties of the sources that we should be, you know, are we giving all the information that our experimental colleagues actually need to then go looking for this, right? And I think isotropy is definitely one of these questions. Now, particular for this frequency band, one question that bugs me, and that I would be curious if anybody has any thoughts about it, is the correlation linked. Because in principle, at these high frequencies, right, we could hope to build, say multiple detectors, multiple small lab-sized detectors, right, to cross-correlate, in particular for stochastic signal. But then, since again the wavelength is so short, what is actually the coherence length at gigahertz, and like, does that actually depend on the source? Does that depend on the propagation, like it is a property of our universe? It's not so clear to me.
Actually, that's an excellent question. I think, for instance, if you think of megahertz, this is 300 meters, right? The wavelength. So gigahertz is 30 centimeters. So in the megahertz, definitely a tabletop experiment, and I will describe tomorrow in the solid state, which are relatively small sizes, will be well within the wavelength of these waves. So if you should see correlations.
I want to cross-correlate, right? I want to take, say, okay, let's say megahertz, right? We take a megahertz detector and we put it, yeah, but let's say we put it 1,000 kilometers apart. Yep. Is that so correlated or not? Over how many wavelengths is the gravitational wave correlated?
It depends what you measure from my point of view, because for Michelson interferometer, you measure directly amplitude of wave. So then you have to resolve the waveform. So in order to cross-correlate, you have to take into account obviously the frequency and to see where the sync function start to, let's say, you don't have more correlation. But if you are converting, let's say, one graviton to photon, this is energy, is an event. So this event will has a, let's say, a timeline, and you have and suppose that after kilometers you have that event time delay. But you don't resolve the field fluctuation, but you just have an energy event. And this can be cross-correlated, even if they are separated kilometers apart. But if you want to then to measure the amplitude of the field that is oscillating your mirrors, then you need to bring the interferometers together. for the inverse Gerderstein effect, like we discussed for Alps, you can do cross correlation because these are events, are energy events, and you just try to compare the magnitude and the timing of the signal. And you don't resolve the field fluctuation, actually.
But that would, Aldo, what you say, that would be true like for the Alps case, right? For the
Yes.
kind of individual event. That would be true for a transient signal, right? Not for a stochastic background.
Yes, absolutely. It will be true for a transient signal and stochastic. And here I have also actually a question for people that who wanted to study this energy fluctuation. Sebastian, maybe? Sebastian class. Also here you showed us the energy that is function of the magnitude of the gravitational field.
Yeah.
This is the inverse Gerderstein effect. So I guess that you are looking for primordial black hole colliding. Okay, and this will have
exactly. Yes.
So you might need to see this energy that goes up and down in frequency, and then it's not clear to me if you will have an energy fluctuation or just a photon with some frequency.
It would more be a burst of energy because well, we have like 10 to minus 10 watts for the signal. And the signal lasts 10 to minus 5 seconds, so it's 10 to minus 15 joule, and I think it's more than one photon.
Okay, so you will see, let's say, these energy bursts of energy that goes up and down.
Yeah, exactly.
And you can somehow estimate the waveform of this primordial. Yeah,
theoretically, yes, but experimentally, I would say that it would be very challenging. Yeah? Because the signal is very short. Huh? It's a microsecond.
Mm-hmm. Okay. Yeah, thank you. It just was a curiosity that came in mind. Right now, we're now that we discussed about.
Thank you.
Yeah. That's all, Valerie.
Can I jump into? I think I'm interested in talking about what Valerie was asking, and it's not clear for stochastic gravitational waves, especially like those coming from inflation or preheating, what kind of coherence we would expect. But if you guys can calculate the coherence length that is expected, that would be good, because you have to place the detectors far enough that the systematics wouldn't be correlated, but the signal would be, right? And for the centimeter scales, if I put them in the same lab, a centimeter away, like all the systematics are going to be the same.
I think it depends very, very much on the model. You know, it's not necessarily a generic prediction of inflation or of preheating. It really depends on the model and the specifics that you can have one correlation length or another. For instance, Juan was mentioning before that preheating would give rise to a totally isotropic background, but in reality there are scenarios in which you can induce anisotropies at cosmological scales, which would mean that if you were capable, even if this very high frequency, short wavelength background could have a modulation looking at completely different angles in space if we had the capability to differentiate the direction. So it really depends on the model, I think. And for inflation, people have worked out things that you have parameters to, you know, tune what is your correlation length, essentially.
And what is
I'd be curious if you have some, if you have some references on that, Danny, I'd be curious, because it's not clear to me, even in like single field vanilla inflation.
No, in single field, I don't think so, because in single field, there is only the standard quantum fluctuations, you know, which has nothing to do with the single field itself, no? And then there, I think it will be purely homogeneous and isotropic, except modulo that background is going to be propagated through the perturbed universe, So at the very least, it will pick up the 10 to minus 5, no? A scalar fluctuation.
Right, but like I'm not asking about homogeneity, right? I'm asking about correlation length.
Yeah, but isn't it the similar in this case?
No, I think I could have a completely homogeneous background, right?
Mm-hmm.
I mean, let's forget about the dipole, right? Let's assume the cosmic rest frame.
Yeah.
I could have a completely homogeneous background, and it's still not clear to me what is the correlation length. Like what? Yeah, no, it's not. It's just not clear to me. It could be. I suspect. So I suspect that if you have something like inflation, you initially have a very long correlation length, and then it probably gets destroyed via propagation effects.
So what is the? I mean, what I expect, no, is from any background from the very early universe through propagation effects, we will pick up fluctuations at the scale of where we have natural fluctuations, scalar fluctuations, no? Is that going to affect the correlation length at the scales at which we are measuring anything? I doubt it, no, other than just looking at very different angles in the sky.
I don't want to look at different angles. I just want I kind of want to. So say LIGO, right? LIGO takes the two detectors, right?
Yeah.
And they cross correlate, right? And they say, I mean, in the ideal world, kind of the cross correlation of the noise drops out, and the cross correlation of the signal is what you look at, right?
Okay.
But now, if I have something, but there has to be an end to that, right? As Nancy was saying, right? I mean, if you put them too far apart, at some point you lose the correlation. And then simply the cross correlation of the signal is going to be 0, 2, and you measure nothing. And the smaller the gravitational wave, the bigger is this danger, right? Simply because the number of wavelengths between your two detectors is growing.
Even if you're looking at the same point in the sky, right? You could fix a point in the sky, you imagine a gravitational wave coming from that point. And that's the question.
Danny, think of time variations in preheating, right? Typically 1 part in 10 to the 30 or so seconds, but this has been time dilated by time dilation through the expansion of the universe. So they arrive to you at different times. So you might be seeing different hypersurfaces, right, with different inhomogeneities. You're not resolving the homogeneities. It looks homogeneous to you in the sky, but the fact that they arrive at different times, because there are fluctuations on time, will mean that when your stochastic background arrives, there will be correlations in time. When this arrives, when the next one arrives, and so on, which have been time dilated by the expansion of the universe all the way to us. And this introduces, well, we have to see what are those correlations in time in your detector, whether you can resolve them or not. If reheating occurred at very high energies, yes, perhaps there's enough of these expansion that can put this into the right time domain. Otherwise, you will integrate over many fluctuations, and again, it's like looking at different angles.
I think I know what you mean, guys, now, or at least what you are saying, Juan. And I think I did the computation with Chiara to see what is the correlation length in time now as coming from the early universe. I think it's 8 hours when it comes from QCD, but it's much shorter when it comes from any higher scale.
It should be shorter than hours.
It should be shorter, and then it looks very, very difficult, no? Because if you are looking at the time signal, you know.
Sure.
Yeah, I don't remember the numbers, but I think in the review we worked them out, and it seemed very, very difficult to see anything from the early universe, at least. I see.
So this is related to the next thing I was gonna say. That
just 1 second. Mike has his hand up since quite a while.
Hey, thank you. People have thought about this quite a bit. There's a very good paper by Bruce Allen some years ago on stochastic backgrounds and how you would try and detect them. And I think there are two things you've got to remember. One is that this is a 4-dimensional correlation, really, because you could have two gravitational wave detectors spaced by many wavelengths. And of course, a time series would be fine. Time series correlation would be fine for a gravitational wave that's coming in the line of direction between the two, but you've got gravitational waves coming in other directions as well. And so when the two are spaced by many wavelengths, I suspect the likelihood of a correlation drops very quickly to 0. The other point I want to make was very quickly that you need to ask yourself, why are you wanting to do a correlation? Clearly, if you can do a correlation, and of course you probably can only do that in situations where your instrument is much smaller than a wavelength, because the instruments we've talked about looking at gigahertz gravitational waves, the waves are a few centimeters in size, but the instruments are meters in size. So when you're doing a correlation like that, if it is to establish that these two detectors are seeing the same signal and that therefore the signal is real and not just some instrumental noise, and if you find that really difficult, and I suspect you're going to, then there are other things you might think to do, which are, and these have been mentioned a little bit, but can you in some way make your detector unresponsive to gravitational waves without changing its function in hardly any way at all? I mean, Andreas talked about switching off the magnets in an Alps situation, but you're looking for such a small signal that even the change in the ambient magnetic field around a microwave detector may affect its noise temperature. And how are you going to convince yourself that's not the cause? In magnetic conversion detectors, though, some of us have been thinking about a means of affecting the sensitivity, really essentially cancelling the sensitivity by tiny changes in gas pressure within the detecting volume that will change the phase velocity and make the electromagnetic signal out of phase with the gravitational signal. So you could effectively turn off the detector without sensibly changing its noise temperature or doing anything else like that. So I think correlations are going to be difficult, and you may need to think of other ways of proving that you've really got a signal.
At Alps, we are doing such a thing. So we are filling in gas in order to change the phase velocity in order to get sensitive to the axion mass, so to say, in a certain region. And so this can be, of course, then also used in this context. In a sense.
Yes, Andreas, we are just trying out whether this is feasible.
Okay.
We hope that we can do it, but we start first tests on this maybe in November.
Okay, good.
Okay, Nancy, sorry, I interrupted you earlier.
Yeah, no worries. I think it's also along the same lines. It's also going to be important for us to think about what is the benefit of integration time if we can't really rely on coherence for these sources. And already the scaling is very non-favorable. It goes as to the 1/4, right? But will it be even less favorable than that if the coherence length is already too short? Yeah, that's all.
Okay, it's starting to get late, but do we have any more questions or comments that people would like to make before we close the session?
I just would like to briefly come back, and Andreas has sent around in the chat. So the baseline, how we could calculate the sensitivity of Alps 2 with this. But someone needs to sit down and then do it really, this detailed work for Alps 2, just to get the sensitivities. That, by just briefly looking at the paper, probably that's not me, but someone who needs to really calculate it. But maybe this could be one outcome of this workshop, that we have someone really in contact with, let's say, with Andreas and me for all the details, to really come down to a concrete number and sensitivity for Alps 2. So I think what Andreas was pointing out, all the ingredients are there, but now we have to do this, all this detailed work to calculate the sensitivities.
Yeah.
Yeah, maybe if you could post, I mean, if you want to, right, of course, but you could also post a bit on what you put in the chat, right, to post it on Mattermost, because the Zoom chat will be gone and dead, right, once we close the meeting. But in case, I don't know, in case somebody is interested, right, then on Mattermost would be a place where they could take it up. We'll also leave the Mattermost channel open, like post workshop. as a kind of a space to connect people a bit.
Good idea. Mike, do you mind writing in Mattermost this reference to Bruce Allen's work?
Oh,
I'd like to have a look.
I'll do that.
Thank you very much.
Sorry, just one last comment, Valerie, because I was checking what I had written with Chiara. So I don't know if this really answers much of the question, no? But the coherence in time of, say, two signals that would come in the same line of sight, okay, but emitted from regions separated away by a horizon distance in the moment of emission, corresponds to 8 hours for the electroweak scale and 9 months for the QCD scale, okay? So in the case of electroweak scale, it would be fluctuating very fast. But for lower scales, there would be a chance to see that correlation.
Right, and I would say that's probably a lower, sorry, an upper bound on the correlation.
That's an upper bound. That's an upper bound because it's based on causality. Yeah, that's right. Yeah.
Right, and also that's kind of that. I think, yeah, right now I understand. Right, this is essentially the correlation at the sourcing time.
Yeah.
Right, and then okay, of course, this now depends also on the model, right? Am I actually sourcing something which is Hubble scale at the time or something smaller, right? Okay. Right. So this we can compute.
Yeah.
And then I think also the question is this correlation rate that we have at primordial times, is that actually preserved? Like do we just redshift it, right? Or does it get destroyed via inhomogeneities in the universe?
Yeah. Yeah, that I haven't thought about it.
Yeah. No, but okay. I think I just found it in your paper. Yeah. So this is. Yeah.
My feeling is through propagation effects, it would get distorted. I would believe in a very small amount at very large scales. No, I cannot think of a signal that has traveled 8 hours, of difference to us, and has been affected by the different potential wells that it's gone through.
No, I'm worried about signals. So say you take two signals which are sourced within a Hubble patch primordially, right? So very close together even.
Okay.
But now they travel to us.
Yeah.
But they travel 13 billion years, right? So they travel many wavelengths.
Yeah.
And what if kind of something on that? So if they followed both the exact same trajectory, right? Then it's fine, right? So okay. So I guess what we are sensitive to is the change in the gravitational potential.
Yeah, I think this is the Satchwell effect, right? This is the Satchwell effect precisely, and that's what I'm saying. That's a minimal effect that is going to be there, but it's expected to be very small, no? Because
but it's small. I mean, it's small for kind of the CMB.
Yeah.
Because it's a question of scales, right? I mean, this is kind of what destroyed our non-Gaussianity project, right? I mean, it's not clear that this is small. I mean, it depends on the scale. I mean, this is small for kind of CMB fluctuations because this is horizon size fluctuations. Yeah. Right. But this is not clear that this is small for like centimeter scale things.
Okay. If there were fluctuations bigger than those at the CMB, you mean, or?
Well, I just mean, like, say you have things which are kind of correlated, right? Which are kind of either like close together in a 4-dimensional patch in the early universe.
Yeah.
Then they travel to you, but they travel like either in time or in space. They travel on a slightly different trajectory.
Yes.
Just because the universe is not perfectly homogeneous in time and in space.
Right.
And then that could induce a phase shift of one versus the other.
Uh-huh.
Yeah. And then that could give you a problem for the coherence.
Okay, could be. Yeah, I don't know.
Yeah, during preheating, however, the time variation could be order 1. So one patch and another, separate by just one horizon time, might have order 1 fluctuations. So as they travel to you, indeed, you're right that if you have a very tiny deviation in the potential well from that moment until us through the intermediate matter, this will decohere. No, these two waves. Okay. But you have order 1 fluctuation, so somehow it's true for a very tiny variation. But for order 1,
but at the horizon size, as you said, Juan. So
horizon size.
We are going to see a solid angle here that encompasses trillions of those, you know.
Exactly. So every single one at a horizon size in time and distance, you know, like Mike was saying, 4-dimensional, the trajectory of those two gravitational waves coming towards you is essentially filling the same potential well.
Okay.
Yeah, but like a teeny difference is enough, right?
True, because it traveled for a long time. I agree.
It traveled for a long time.
One
right?
has to compute that. I agree. I agree.
Yeah.
I agree. You know, I remember the project we had together.
Yeah. we learn from our mistakes.
We
right?
learned. Yeah, really.
Okay.
Just a quick question, Valerie. Why are you worried about the coherence of the source?
Well, for essentially, I'm wondering kind of if we can use multiple detectors to distinguish kind of a stochastic signal from a stochastic noise.
But when you have detectors, you just make coherence of their signal. You don't make coherence of a wave that is emitted from the source.
Well, I'm thinking, say LIGO, right? So for LIGO to detect stochastic background, right? They cross-correlate the noise, right, in both instruments.
Yes, they cross-correlate the noise because the gravitational wave takes some time to propagate to the next instrument. So they are perfectly coherent. So they are moving perfectly coherent, the differential arm length in same wave. That's fine because you are measuring the amplitude. But if it is stochastic, what's the problem?
No, I mean, the way, I mean, the way you essentially, like, the way they kind of measure stochastic signal is by essentially just taking, say you have some noise, right, which you don't know exactly, is this instrument noise or is it actually a stochastic background noise, right?
Yes.
Like Penzias and Wilson with their radio telescope.
Yes.
And one way to check, one way that whatever Penzias and Wilson could have checked if their noise is instrument noise or actually kind of cosmological noise is by having two instruments and you cross-correlate this noise.
Mm-hmm.
And then in an ideal world, the noise, when you cross-correlated, the cross-correlation would be 0 because the noise is independent.
Mm-hmm.
But for the signal, it's not the case, right? So for the signal, the cross-correlation would remain.
Yes.
And exactly, and I'm kind of wondering at high frequencies that we're talking about,
yes.
Can we play the same game or can we not play that game because
no. If you measure the amplitude as the LIGO does, no, you can't. As you go above the gigahertz, you need to bring them centimeters apart, close to each other. Otherwise, you are losing coherence. But if you go to high frequency, the same thing. But for example, for magnetic conversion, as I said, you transfer energy from gravitational wave to photons. So you have the events, and these events, let's say the photon obviously has its own electric field oscillation, but what you measure the energy of the photon in time, and second later you will have another decay further away. So this can be correlated.
Yeah, but this is transient signals, right? But I'm worried about stochastic signles. Stochastic signals.
Stochastic will generate the same thing. Suppose now you have many of these transient signals that are happening at the same time in any direction. So I see stochastic as an uncorrelated transients. You see what I mean?
It is not entirely uncorrelated, right? I mean, this is otherwise, if it were entirely uncorrelated, LIGO could not detect it in the way that they are detecting it. Well, they haven't detected it, but they couldn't look for it in the way that they are looking for it.
No. The stochastic is correlated, let's say. So you suppose that you have a stochastic. I guess the coherence length of stochastic is for LIGO is higher than the distance between them.
Yeah, right. But this is exactly the question I'm asking, right? I mean, I understand that, like, obviously that you have a finite coherence length, and if you put the detectors too far apart, then you lose coherence, and hence you lose the correlation. And I also understand that kind of the higher the frequency, the shorter is this wavelength, or the shorter is this distance. But I don't know a number, like how like say I'm looking for gigahertz waves. How far? What is?
Yeah,
is there a sensible optimal optimal separation of the detectors?
If you look to the coherence, you have this sync function that depends on the frequency of your gravitational wave. So it's like you lose coherence as you go out of phase of 45 degrees or 90 degrees, something like that.
All right, but this is just the overlap reduction function, right? But this is not what I mean. This is the overlap. To compute the overlap reduction function, you're assuming coherence. So this is not what I mean.
Yes, I understand what you mean. So you are worried about the coherence of the source.
Yes.
So if the source change phase, you are lost there. You have to assume that the source is coherent over that length.
Right, and my question is about the theory prediction for the coherence of the sources, because I think that is something which is not.
I can't say nothing about the coherence of the source. I assume they are coherent for a long time because I don't know why, but.
Yeah, I think my point is kind of, I think this is a question for theorists, right? This is kind of a homework exercise, and then maybe as Mike and as Danny have said, right? There's already
imagine now, when two LIGO interferometers, they detect the same signal. I assume they are coherent. So
so I think this is an exercise, I think, for the theorists, including myself, based on the literature that was mentioned, to maybe find an answer to this question.
Yeah. Clearly, the answer to your question is people need to calculate it. I mean, what I'm hearing is nobody has calculated it or has any serious idea on that. I know everything you've said about whether a detector can detect coherent sources 2,000 kilometers away or centimeters away. I mean, all that is true. I just add a comment that if we could make a Sirius terrestrial source, then we would know that that's coherent over a much longer coherence length. But as I said earlier, the technological problems in doing that are at least as serious as making a seriously sensitive UHF-GW source.
Can I just chip in that the paper, I put it on Mattermost by Bruce Allen, has got some very simple arguments about the coherence length of cosmological sources at the beginning of it. So it's worth just looking at that and seeing whether you believe those arguments.
Okay, fantastic. Okay, so thanks everyone for the nice discussion. And so tomorrow we start earlier, so as to accommodate some of the speakers from Asia and Australia. So we start tomorrow with the discussion session at 10, and then the first talk is by Richard at 10:30 European time. See you tomorrow.